All right, ladies and gentlemen, we are going to be doing skill 31B, which is the mean value theorem. And I decided to give this its own separate day since this one is a little bit more involved computationally. The computations are very doable, but basically what the mean value theorem says is that assuming that we have the conditions of continuous and differentiable, there is a situation as long as we have, continuous in a closed interval and differentiable in an open interval, where the instantaneous rate of change is equal to the average rate of change. So some conditions do have to be met. So what does have to happen in order to use this theorem is the following. So it has to be continuous in a closed interval. And it has to be differentiable, meaning that I can take the derivative in an open interval. And if those conditions are met, then we can use the mean value theorem. So what I mean by that, and what can kind of happen sometimes, with the continuous and differentiable assumption, an example of continuous not differentiable something that's like kind of absolute value, like, so like where there's kind of corners and stuff, is definitely a situation where we could kind of see that maybe the instantaneous rate of change would not equal to the average rate of change. So like if I did, like A to B, my average rate of change is 0, because I'm not changing in Y value, but there's no place where the slope is 0. All right, so there's two types of delta math questions we're going to be looking at. The first type is sort of that always, sometimes, or never. So the first thing that you want to do is look for the assumptions. So I will say that you cannot say true if the assumptions are not true. And we can see here that this is pretty nice and well behaved. So we have the continuous interval and the open interval. So it's continuous and differentiable. Now, if it's not continuous and differentiable, this is not to say that it will be never true, but we just cannot guarantee that it's always going to be true. Okay, so our assumptions of continuous and differentiable are good. Now, let's look at the average rate of change and compared to the instantaneous rate of change. So we are looking to see if there is an X value for where the average rate of change equals to 3, negative 3. So that's your instantaneous rate. So let's actually kind of compute some average rates of change. So I could look at, let's see, our formula for this would be, f of 3 minus f of 0 over 3 minus 0 equals to negative 3. So I have 1 minus 10 over 3 minus 0 equals to negative 3. And you could just like put little question marks over the equal sign. And what I see here is I have negative 9 over 3 equals to negative 3. And it looks like it is going to equal that. So the answer is always true. All right, let's take a look at another one, maybe one that doesn't quite work out as nicely. You're going to see some where the assumptions of closed, continuous, and differentiable on the open are not there. So that's going to be kind of guaranteed to be sometimes true. But for this one, we're going to kind of see what happens with the behavior here. So we want to see, that the instantaneous rate of change and the average rate of change are matching. So here, the instantaneous is 1. And I like to say average rate equals to instantaneous. So what we're going to kind of do here is just look at the overall average. So I'm just going to kind of look at the different possible intervals. So I'm going to look at 0 to 4 first. So for this one, I want to see, does f of 4 minus f of 0 over 4 minus 0, does that equal to 1? So I'm just going to plug in, negative 21 minus a negative 5 over a 4 minus 0. And let's see, for this one, I think it's pretty clear that we're not going to settle. I got negative 16 over 4. This does not equal 1. So far, not so good. Now we're going to try another interval. So maybe I'll try, 0 to 1. So on this one, I'm going to do, f of 1 minus f of 0 over 1 minus 0. So that's going to be negative 6 minus a negative 5 over 1. And I want to see, does that equal 1? Because our goal is that the average does equal to the instantaneous. So if we do get an average rate of change that is in line with our instantaneous rate of change, there is that x value in that interval that we could call C. So let's see, I got negative 6 minus a negative 5, so that is going to be negative 1 over 1, which is negative 1, and that is not equal to 1. All right, we have one more chance to get that average rate of change. So I'm going to do f of 4 minus f of 1 over 4 minus 1, and I'm going to see, does it equal to 1? So I'm going to plug in negative 21 minus a negative 6 over 4 minus 1, and does that equal to 1? So in this case, it's going to be negative 15 over 3, and that's negative 5, which clearly does not equal to 1. So it's not going to be always true. However, it is entirely in the realm of possibility that it could happen. What we are kind of seeing here is that our slopes are going down, but there's no language about it constantly being, decreasing in slope. So, I mean, we could have, a situation where maybe it goes up when x equals 2 or x equals 3. So it's not entirely eliminated. So we would just say sometimes true. All right. Now we're going to look at another type of example here. So this is actually finding the C for which the mean value theorem works. So it is kind of a wordful here. So this says the function f of x is equal to the polynomial expression. So we always give you a polynomial function, is graph below. Plot a line segment connecting the points of f where x equals negative 4 and x equals to 1. So I'm going to go find where x equals to negative 4 with my mouse. And then I'm going to go find where x equals 1. And I'm going to plot the line so that it settles right there. And this is our average rate of change. The slope of this line is our average rate of change. And the question is there a x value for where the average rate of change is also the instantaneous rate of change? So we can kind of see that it's kind of a downward slope. Notice that the scaling is on there as well on the graph, and it's kind of in increments of 10. Okay, so our goal here, and the way that we are going to set this up, we are still going to do, average rate of change equals to instantaneous rate of change. So I always like to think about that. All right, so the average rate, this is where you are going to do f of 1 minus f of negative 4 over 1 minus negative 4. And then the instantaneous rate of change, this just means take the derivative. And what we'll do is we'll just take the derivative. So this would be, f prime of x symbolically. I'm going to suggest that we use our calculator to help us out. So I'm just going to go to our Delta Math calculator to help us out here. I'm going to enter my function. So instead of putting, I'm going to evaluate f of 1 first. So I'm just going to plug 1 into my original function. So I'll even just kind of like demonstrate the plug-in here, for instance. So like if I have 1, this is where I put 1 cubed plus 10 times 1 squared. plus 13 times 1 minus 4. I know it's been a little bit since we have done the instantaneous rate of change. So we're going to put in the average rate of change. So we're going to actually put 1 cubed. And I like to put the parentheses in there. And then this is 10 times 1 squared plus 13 times 1 minus 4. And the value that we get on that is going to be 20. And actually, it so happens to be 20. But I think it's always good to just kind of be safe and plug it into the calculator in case if it's like 21 or 19. So then I'm going to substitute in -4 instead. So to find out what f of -4 is. And when I do that, I get that that is equal to 40. So I have actually done all that I really need, I think, on the calculator for now. And then 1 minus -4 is equal to 5. And I might as well just take the derivative of the function. So the derivative of the function is going to be 3x squared plus 20x plus 13. All right. So I'm going to take that calculator away now. And this actually is settling nicely into, algebra 2 style math at this point, because 20 minus 40 is going to be like -20 over 5. And this is going to be -4 equals to 3x squared plus 20x plus 13. And I'm just going to solve this like I would, an algebra 2 type of problem. So this is going to be 0. So I want to make sure that I get everything equal to 0. So I'm going to move that 4 to the other side. So I have 3x squared plus 20x plus 17. So now I'm going to factor. So I have 0. And I know that there's going to be, you may want to just do like the ACB chart. But when this is factored, what we will actually get so we will get, 3x plus 17 times x plus 1. And then, of course, you want to do the 3x plus 17 equals to 0. So I get 3x equals to minus 17. So I'm going to divide by 3. And I get x equals to -17 over 3. Or if we were to kind of see what number that is, that would be about -5.33. So I'm going to cross this one out, though, because it is not in the interval. And then on this one, I'm going to say that x plus 1 equals 0. So I'm going to get that x equals to -1. And that does happen to be in the interval. And if we look ever so closely, and I'm just going to draw a tangent line right there. And it does make sense that at -1, it does work. So that is our value of C. So that's just, what we get when the average rate of change is equal to the instantaneous rate of change. And we are good. And what we can kind of see when we are looking at the solutions, we can actually see how they plugged them in, which is very, very good. And how the average rate of change was computed and the factoring process. And I think what's also awesome, we can kind of notice here, is that the instantaneous rate of change is exactly at -1, and that matches our average rate of change. And we can tell that because they are parallel to each other. Shall we see one more? So let's just do one more right now. This function here is a cubic. I have x cubed minus 14x squared plus 56x minus 64. So I'm going to connect 1 and 4. And what I may want to do is I may want to kind of think about where it is that it's parallel, and that kind of gives me maybe an approximation for where maybe that average rate of change is matching that instantaneous rate of change. So I'm thinking here that it's probably going to be around 2 or 3 for the value of C. So I'm going to fire up the Delta Math calculator here, and we are going to go forth and compute. So we've been a little bit more around the block now on this. So the first thing that I'm going to do is I'm just going to say that the average rate of change equals the instantaneous. So average equals to instantaneous. And so the average would be f of 4 minus f of 1 over 4 minus 1. And then the instantaneous, I might as well, at this point, just take the derivative. So that's 3x squared minus 28x plus 56. That is the derivative. And then I'm going to find out what f of 4 is and what f of 1 is. So I'm just going to plug in a 4. So I'm going to say 4 cubed minus 14 times 4 squared plus 56 times 4 minus 64. And that gets me exactly 0. And then I'm going to go and I'm going to see what that is for f of 1. So I'm going to just replace the 4 with the 1. So I have 1 cubed. And I'm just going to put in 1s instead. And that gets me to negative 21. Over 4 minus 1. And then this should simplify to a number. So this is actually just going to be 21 over 3. So this actually simplifies to 7. And I have something that looks like an algebra 2 type of quadratic that I need to solve. That's where we're going to kind of end up quite a bit on these. So I want to make sure that I am setting this equal to 0 before I solve. So I have 3x squared minus 28x minus 49 equals to 0. And the question is, how do I solve this? And one shortcut that you can do actually is if you go to a like a quadratic calculator. That's a shortcut, you know, when you kind of have these big numbers. I don't object to you doing that. So in a minute, we will be at a quadratic calculator. So I'm just going to pause for a moment. So what I did is I actually just entered my coefficients in, so the 3, the negative 28, and the 49. And this one, you know, definitely has bigger numbers like on the ACB chart. Sometimes you may get one where you have to do a quadratic formula, which is, you know, kind of ugly. But what we do see here is that it becomes 7/3 or 7. So if we go back to our, and this is a plus 49, I forgot to put the plus sign here. So our answer would be 7/3. And the 7 is not in the interval. So you always take away the one that is not in the interval. So you're just going to be choosing the one that's in the interval. So 7/3 is about 2.33. But they are going to want the fractional nature of it. And if you look, I could even estimate what the tangent line is at 2.33. So right about there is where we're looking at. And the tangent line seems to be kind of right parallel. And we should be in pretty good shape for that. Make sure that you're putting it in fractional form and not rounding because it will be a little picky on that. And we are good. So, and we can kind of confirm with our graph. So it's about 2.33. So if you do want to save a little time, you can always go to the quadratic calculator if you don't want to do like crazy big factoring and stuff like that. But what I do care about is that you are looking at average rate of change equals to instantaneous rate of change. So thank you very much, and looking forward to seeing you practice this.